Today I'm going to explain you about the rod cutting project. So first, the main problem definition here is we have to find a way to cut the rod to maximize the revenue while ensuring that the sum of the lengths of pieces is equal to the length of the original rod. So here I have given the objective, and the main objective would be to determine the maximum revenue that can be obtained by cutting the rod into pieces, and the length would be like starting from 1 until n. So here we have some real world applications that includes manufacturing department, finance, industry, forestry, metalworking, and also packaging. And when we come to the algorithms, here I have taken two algorithms to implement this, and first one would be brute force approach. Here I have mentioned a few steps explaining how I implemented the algorithm. So moving to the code, so this is the code which I implemented using brute force method. So here the code is an implementation of rod cutting problem using brute force recursion. As I already said, it is to find the maximum revenue that can be obtained by cutting a rod, and the main function here is rod cutting brute force is the that implements the brute force recursion. It takes two arguments, n, the length of the rod, and the price list. And next is the time brute force list is used to store the empirical runtimes of the brute force algorithm for different values of n. Next, there are n values here in these n values I have taken small values to show the output from 1 to 9. And next, it contains different values. We can choose any values. According to that, the empirical runtime will be like different. And now if we run this code, so here we can see for as the time complexity of this one brute force is 2 power n. So that's why if we take 1 2 3 4 5 6 8 9, it will square the value and will be giving theoretical complexity. And here is the empirical runtime, and here would be the ratio between empirical and theoretical runtime. And when we go here to find the predicted value, here we can see so this is the brute force. In order to find the predicted runtime, we have to multiply ratio with theoretical complexity. After that, we'll be getting the predicted runtime. So next algorithm I have chosen is dynamic programming. In the dynamic programming, I have chosen to do the bottom up order. Here we have to initialize a list of size n+1 to store the maximum revenue of each rod and each rod length. And the runtime analysis of this algorithm is n power 2. So if we go to the code, here I have explained about the algorithm. Here the code measures the time complexity of the dynamic programming of rod cutting problem. The rod cutting dynamic function is the main one that uses dynamic programming to solve the problem. It relatively calculates the maximum revenue for rod lengths from 1 to n using the formula revenue list of I is equals to maximum price of list j minus 1 plus revenue list 1 minus j. So that's the main formula we have used here, and the code then calculates the theoretical and empirical time complexities for each rod length. So now if we run this code, and before going to the output, here I have taken the n values of from 10 to 50 in 5 times. So here if we see for each value we have taken as time complexity for this is n power 2, the number would be squared, and after that we'll be getting the theoretical time and also empirical time, and for the ratio empirical time by theoretical time. In order to find the predicted time, the same formula can be applied. That is we can multiply the empirical runtime, ratio, and if we multiply with theoretical complexity, we'll be getting the predicted runtimes. So here we need to consider the maximum ratio wherever that is, because in this ratio the highest value is 0.000912, but instead of since it is an outlier, I have chosen the next maximum value, and I have multiplied this with theoretical complexity to get the predicted runtime. So here it is the graph for this dynamic programming plot. Here we can see these are the n values I have taken, and here it is the time. And for the brute force method, here are the n values, and here is the time in milliseconds. So according to that, the plot can be drawn. So next, the conclusion. So the empirical results shows that the running time of dynamic programming and also brute force, when compared to dynamic, brute force approach is slower, because as the input size increases, which is consistent with theoretical time complexity, so the theoretical time complexity of dynamic is n square, and the brute force is 2 power n. So thank you, Professor.